It's a pleasure to be here. Today I'm going to talk about from the 2025 Nobel Prize to tabletop cosmology, superconducting quantum circuits as detectors of new physics. So you might know that the 2025 Nobel Prize was won by this combination of physicists, John Clark, Michel Deboré, and John Martinez. And the work that they did has a great opportunity to enable us to study new physics. So this is our group in Perth. We're the Quantum Technologies and Dark Matter Lab. We're part of the Dark Matter Centre run out of Melbourne. Currently, we've got 4 academics now. It used to be 2, now we've expanded since our success with centres. We have 3 postdocs. We have 7 PhD students and a bunch of undergraduates, and we take on a lot of vacation students who usually progress through the doing honours and PhD. If you're interested, you can, thanks to the old centre we were involved with, Equus, that you can do a lab tour, a virtual lab tour online if you go to our webpage. We have a lot of different equipment. Particularly, we have 3 dilution fridges from Blue Force, and we have a bunch of superconducting magnets and a large collection of microwave and diagnostic equipment and experience with precision metrology and testing low noise systems. So I would like to say to you, physics is an experimental science. And I like this quote, "One accurate measurement is worth 1,000 expert opinions," because that's what experiment does. And that was said by Grace Hopper. Who knows Grace Hopper? Who's heard of Grace Hopper? Put up your hand. Quite a few. That's good. She was a computer scientist and she invented COBOL. Put up your hand if you heard of COBOL. It's becoming a lost science, this programming like that, Fortran COBOL. We've got other things we can do. And AI just programs for us now anyway. So anyway, I like that quote, and coming from a computer scientist, the point is the better inputs into our simulations, the more accurate we can be with predictions. And in the end, physics is an experimental science. So in our lab, we do precision metrology. We do photon systems, historically go back to these high-Q sapphire resonators. Currently, we're building some tunable ones for dark matter scanning. We've looked at spins in solids. There's a big push for spins in solids for quantum technologies. And we've done a lot of work with magnons and spin waves, and we use these acoustic systems as well, bulk acoustic waves. In the end, we use techniques to measure these in very low noise. And so how does this relate to the Nobel Prize? So the Nobel Prize demonstrated that superconducting circuits can feature macroscopic quantum behavior. And they were awarded for showing that a lump of metal basically on a chip can behave like a single quantum particle and tunnel through barriers and occupy discrete energy levels. This is the foundation of modern quantum technologies. Whoops. Got to get used to using my mouse here. And this was the paper where they described this first. It was just a PRB, I could say, and there's the 3 authors from Berkeley at the time. And they did a Nature Physics articles about quantum Josephson junction circuits and the dawn of artificial atoms. There I go again. So here's an example of a cartoon that shows one of these junctions with 2 pieces of metal, and the junction creates this nonlinear inductance, which you can then read out. And the point is that there's a potential, and this potential has a cubic-like potential, and it's not your normal harmonic potential quantum mechanics problem as you have in second year. It's now anharmonic, and it means that these energy levels have different values. And what they showed in this paper was that when you had something in the ground state, the energy was different to if you had two particles in the occupying up to, or if you had a higher energy, if your particle went up to a higher energy state, sorry, and up to even higher, that the energy would change and would not be the same, and therefore could be distinguished. And this what enabled this new breakthrough. And this was traditionally seen in the microscopic systems at the time: atoms, nuclei, electrons, and semiconductors. So this prize is about doing it with billions of Cooper pairs acting as one macroscopic degree of freedom. And that is this phase difference in this Josephson junction acts like this quantum system. So this was published an editorial in Nature, the prize at the end of the quantum tunnel, and it highlighted that this 2025 work is based on a prior Nobel Prize, which was the actual Josephson junction. And what they point out that it's likely that research built on the foundation contributions of the 2025 prize will lead to another prize in the future. So they're saying that there was a Nobel Prize which led to this Nobel Prize, and they believe this Nobel Prize will lead to another one. Okay, if that makes sense. So that's one of the things that they look at. They believe so. This is a real expansion area, which will probably lead to more Nobel Prizes. What we do with these quantum technology? Maybe dark matter will be detected. Maybe someone will build a quantum computer. So this showcases the progress of ideas and applications in science that each generation builds on the success of the previous one, and together they move forward. So John Clark, we've co-authored 10 publications with him because he's part of the ADMX collaboration. We work with John Clark in this collaboration to search for axion dark matter. And Maxim Goryachev spent 3 months in his lab developing technology for our lab. And John Martinez, we co-published a paper with him on losses in substrates, because when we went to visit him, he was using sapphire, and we were expert in sapphire to measuring the losses, and he wanted to know the loss at 1 phonon level. So we did an experiment with his guidance, and we co-published this paper. And when he was with Google, we were going to work with him then as well, but then he left. So here's an example of one of our ADMX papers. You can see John Clark is very much part of this. Here's the paper we wrote on with John Martinez. So the point is, our goal has been always to test fundamental physics, and this technology is very important in what we do. So here's an example of some of the technology that he built, this SQUID amplifier. And you can see this SQUID here with 2 junctions, and you look at the interference pattern between them, and you can bias yourself at this point and make an amplifier. And these amplifiers, pretty much as you cool the physical temperature, you get down to the quantum limit in these devices. And so what we needed to have for ADMX is we need to have tunable amplifiers. So you in your circuit, you put a varactor which enabled tuning. So when we scan for dark matter, we can amplify the signal at the frequency that we want when we're searching for dark matter. Here's an example of when they first got funding. They had SQUID amplifiers boost search for the universe's missing mass. This was an article with John Clark. And Maxim built this device in Berkeley. And we built this device because, I'll talk about this a bit more later, we wanted to amplify signals from these acoustic resonators. This is a quartz resonator. It's like the phonon equivalent of a Fabry-Perot cavity, where your phonon modes are trapped in the middle here, and then piezoelectricity puts a current into this SQUID, and then we amplify the signal. So we built that, and we'll talk about it more later. So basically the phonons, there's a radius of curvature, and we needed the SQUID amplifier to read these at the quantum limit, and we indeed, at 4 Kelvin, we could read the thermal Nyquist limit coming out of these devices. We proposed that we could use this as a megahertz gravity wave detector. It's like a little acoustic resonant bar. So we're using these technologies to do precision tabletop experiments. So I'm going to start talking about that. And if we get quantum enabled, we can measure at the standard quantum limit, and then we need to surpass that and do sub-quantum limited to succeed in measuring dark matter. So our motivation is fundamental physics. Over the years, we have done many experiments looking at these parts of fundamental physics, trying to extend the standard model. Lately, we're doing dark matter, high-frequency gravity waves, and what we need to do is use quantum measurement. But we've done a bunch of other things too. Can't talk about everything. Most of you might know what dark matter is. Dark matter is this extra mass that we see in the galaxy and in other parts of the universe, and from a lot of different measurements, I'm no astronomer, astronomers in the audience will know better than me, that it must be a particle. So we know it's a particle, but what type of particles open up for debate, and that's what our centre debates about and tries to understand. Will it interact with standard model particles? Can we convert the dark matter into something we can measure? And that's what we're trying to do. So here is a typical diagram of dark matter. We write the mass in eV. When I first came across, coming from different backgrounds and tried to think of mass in EV, it's like getting used to natural units. You eventually get used to it. But the mass in EV up at these high energies, it looks like particles. And at these low energies, we used to call these WIMPs and WISPs. The community now likes to call this wave-like dark matter. That's because in our experiment, it looks like a wave when we try to measure something. So this is at these lower masses, and this is where ADMX will look for dark matter, and we have our own organ experiment. So the generic experiment will be, we need to design a physics package. You need to make it sensitive to the type of dark matter of interest. It could be an axion. A dilaton is a scalar dark matter, so the theorists have to tell us the models, and then we try and work out whether we can measure it. So we need to know the theory, how it interacts with experiment, and how it interacts with standard model particles. And then we need to reduce noise. Then it becomes a low noise. And the fundamental limit is quantum noise, and you might be able to get below the quantum noise, and that's using quantum metrology and using these detectors based on quantum principles that the Nobel Prize was won for. So we have a program at UWA. We're part of the ADMX collaboration since 2019. That's the biggest axion experiment, dark matter experiment. I'll soon try to explain what that is. And we run this dark matter experiment called Organ, which is the first haloscope above 15 gigahertz. And we have this other one called Upload and Anion, which uses upconversion, a different principle. And we also look for scalar dark matter. You can use spins for phonons and photons for this. And we can use magnons as well. We've done all these type of experiments, and we can go to low frequencies and just use LCR circuits. So there's a bunch of experiments to catch all the different masses. But let me explain axion dark matter, because this is one of the biggest candidates. The reason the axion is popular is because it solves the strong CP problem. And that's why a neutral particle, which is made of charges, doesn't have a dipole moment. It's also, if you believe in the axion, you can see people predict that it to be formed in the early universe. It can solve things like inflation, can solve matter-antimatter symmetry. So the question is dark matter an axion? It's one of the favorite candidates. It's called an axion. Frank Wilczek dubbed it the axion because his mum used to use this detergent called Axion. And when he told me personally that he thought, when he was a kid, he thought it would be a good name for a particle. And when I was a kid, I wasn't thinking of particles, but, you know, let alone did I know what sort of brand of washing detergent my mum used, but or dad. So here we are, and what we do with one of these experiments, the axion will couple to two photons through this coupling parameter GA gamma gamma. And so the stronger this is, the stronger it will couple to these photons, of course. So we make one photon a DC magnetic field. That means it's got zero frequency. And what this enables you to do is this axion will convert into a frequency through E equals mc squared and h cross omega, and then you can just, to try and discover it, you can tune a frequency. So here is the formula of the frequency. You can see E equals mc squared, plus there's some dispersion due to velocity. This is known as a Sakivi haloscope, named after Pierre Sakivi, who first came up with the idea. But the caveat of this is that your two photons here must have non-zero E dot B. So when you integrate over the electric field in your resonator and the B field here over the volume must be non-zero. So that limits the modes you can use in this tunable device. And there's this other, recently, in quantum electromagnetodynamics, that's if a monopole exists at high energy at the gut scale, say, there can be extra portals to coupling. That's through duality, okay? You can have extra coupling. So not GA gamma gamma, which through our known electrodynamics, if we have the joule of electrodynamics because of the magnetic monopole, you can have this GABB or the geometric mean. What I like to say is when you look at the electrodynamics and what is modified by the axion, if you have an axion background field, it brings chirality into your electrodynamic equations. If you look up electromagnetic zilch, this was first discovered and it was called zilch because the person who discovered this conservation law, which is a tensor equation, but it's still a continuity equation, conservation law, he found that whatever he put in there was zero because he was putting in fields without helicity, without right-handed and left-handedness, and so it always looked zero. So he called it the conservation of zilch. So what sort of experiments we do? We do these haloscope experiments with a background DC field, and we scan around the frequency of our resonance, which is reading out, and the mass will be just the frequency plus this delta F, the frequency of this resonance plus the delta F that we scan. That's using natural units, of course. But another thing we can do is this up-conversion experiments. If we make the background field AC, then you get up conversion and down conversion. The down conversion is not sensitive, so this up conversion limit tells you where you up convert a low mass axion to high frequencies is actually an interesting experiment to do. So your mass is now the difference frequency of your readout plus your other cavity, and you can go to lower mass by looking at the difference between two modes. So that you can have two modes in the cavity. One can have a longitudinal electric field, another a longitudinal magnetic field, and as long as the integral of E dot B does not go to zero over the volume, it works. So we can do those too. So there's two types of experiments we can do. One with a DC field, which just gives you the mass equal to frequency of your resonator, which you're tuning, and the other one, which you can excite two modes in one cavity and look at the difference. More interestingly, these axion experiments were shown in 2022 that it also works as a gravity wave detector, a high-frequency gravity wave detector. So what this paper showed is that if I have a background field and then a gravity wave goes through it, there's a similar two-photon interaction, and your sensitivity to this theta, this theta is just your GA gamma gamma times your scalar field. That's how many axions there are, basically, the magnitude of that axion. That's got no dimensions because they've got inverse dimensions, this GA gamma gamma and A. And so that's like the strain sensitivity for a gravity wave, which has no dimensions as well. They identified that it was about as sensitive to axions as it was to gravity waves. So that was a big deal, in my opinion. And there's these white papers on high-frequency gravity waves that we know. One was done a few years ago, and there was an update just published in 2025 with more authors that we were involved with. So here we have some typical detectors. We have LIGO here. We have ADMX, which is cooled a cavity to much lower temperatures. We have Organ, our experiment. MAGE is our acoustic oscillator, which is looking for high-frequency gravity waves. We have Niobe. I don't know if you've heard of Niobe, but I did my PhD on this, and there's the reason why I travelled to Perth was to work on a resonant bar gravitational wave detector with David Blair, and that was basically my PhD project, working on this thing. So these are all got built for specific purpose, but it turns out that LIGO is sensitive to dark matter. A lot of people might know that. This MAGE detector is sensitive to dark matter too. Scalar type of dark matter, probably similar types of dark matter at different frequencies. And now I've just told you that ADMX and Organ, which are axion haloscopes, are also sensitive to gravity waves. And Niobe, if we cooled it down again, would be sensitive to a type of dark matter as well. So the point is, when you build a high precision detector, is that for a built-in purpose, there's always other things you can do with it. And that's what is very interesting and keeps a lot of people busy. And this was my PhD project. You can see when I went in '89, after taking a year off, I went there to do a PhD. And this is very interesting because it's still relevant for today. Here we have a 1.5 ton niobium bar, which resonates at 700 hertz. It's coupled to another acoustic oscillator at the same frequency, which acts as a displacement amplifier. And then we use all these low noise cryogenic electronics, which is still how today we do what we use when we use a dilution fridge. We have hemped amplifiers and things like that. So this was my PhD project, and everything I do today comes from learning from this project, which was, I went and did a PhD over there for half the money. I could have stayed here and worked on a more boring project, but I thought I'd go over there. Moral of the story is, do what you're interested in. Don't accept more money to do something boring. That's my advice, but some people might think differently to me. Anyway, what we see, we have this theta term, which is on the order of Hg. This enabled me to do this paper from my group, which could compare gravity wave detectors to axion detectors. And this has nothing to do with sources. It just shows the noise in the detector, either related to the strain, so we've got strain per root hertz, or theta, which is Ga gamma gamma times the scalar field in terms of noise per root hertz. So units per root hertz. And we can see LIGO here. If we went to high frequencies, there's resonant things you could do to make it a bit more sensitive, but LIGO is not very good at getting high frequency gravity waves. These experiments which look for axions are not really worth doing because they're low frequency. You could easily do something much better. But you can see ADMX and Organ here, which we work on, are actually in their bandwidths, if we can tune them, can be quite sensitive. And this is MAGE here that we're also working on at megahertz. And this is in the signal to noise. If you know that this is the signal and this is the noise, and when you do an optimum filter, this is a signal to noise you can get. So we have this Organ experiment, which is at the moment, Ben McAllister moved out from our group to Swinburne and started a group there under the Dark Matter Centre. So now we've expanded out, and we have also ANU and Sydney people have been helping us here and there. And so this shows you your typical axion haloscope, where you have to have the problem with when you've got non-zero E dot B, you can't, all the modes in your cavity do not tune with length. So you can't tune it with a plunger. You have to change the radius, but that's impossible. So instead, what you do is you put a tuning rod in there and move the mode around by moving the rod. So that's how they tune it. It's not optimal, but it works. And then you use all the typical low noise readout system, similar to what I showed on the gravity wave detector, but using more advanced technology like Josephson parametric amplifiers and quantum technologies. So it's the quantum technologies in the readout chain that I believe will enable us to get to the limits that get to the sensitivities we want. Okay, so the Organ experiment was the first high-frequency axion haloscope, and this is where Organ looks. You can see our measurements here, and our goal is to get to the QCD limit. This shows you the GA gamma gamma you have to get to test the QCD axion. This assumes that all the dark matter around us is axions, and we've published papers there, and there's another experiment, Mad Max, which is working around there, but we're sort of in front. And then we decided to build an experiment around 6 gigahertz because we could test our quantum technologies around here. And indeed, we've got near quantum limited performance there. And we're also looking at these low frequencies, and there's a prototype experiment being built at Swinburne for this. And Pierre Sakivi, who invented the haloscope, believes the axions here. He's got his reasons. But why are we looking here is because lattice QCD and this SMASH model predicted to be up here. But in the end, it's predicted to be in this range, so this is where we should look. We can also look for other forms of dark matter. We've done limits on dark photon scalars and things like that. So we've done that with organ. I just show that to show that when you've got a detector, you can look for more than one thing. So what is the future of the organ experiment? We want to do this 15 to 50 gigahertz scan. We've got a parametric amplifier from Yale, from Hong Tang's group, and our next run will dig down deeper and broader, and that's getting built right now, and we'll start this year. With organ Q, we've already done this scan here, a quantum limited sensitivity. This was the readout, and here's the cavity we built, the tuning curve. I highlight here this Tarse experiment. Last year, it made a claim of a signal. So I'll show you that next. Yeah, so there was this paper on the archive which showed this signal. This was in July 2025. They reanalyzed some old results, and this is a dark photon signal, not an axion. So it's a signal what happens when you don't have a magnetic field. It could be due to kinetic mixing. And it was persistent on rescan, and it was not found in the lab, only in the DR. So they put this on the archive, and Ben from Swinburne and Aaron wanted to do an experiment. I was a bit dubious at the start. Then I said, okay, why not? And we did this experiment. We just repurposed organ, and we put a different tuning mechanism to make it a specific frequency with a sapphire rod. We custom made all this and cooled to 25 millikelvin. We used a HEMT. We had a 20,000 Q, and our form factor to axions was 0.67, 13 days. And we published this paper, this follow-up search. There's our frequency tuning that covered the same range as that experiment in Taiwan. And we got to better sensitivity over the range, and we saw nothing. So we could test it very quickly, and it's published now at the start of this year. And at the same time, Haystack, a big collaboration at Yale, did the same thing and found nothing as well. So the point, what this shows is that if there's any detection in any of these experiments, a whole lot of people can all of a sudden stop what they're doing and try and confirm. And this is really important. I can tell you if the axion's detected tomorrow, I'll stop everything in the lab, and I can do 6 experiments, one with magnons, one with different types of cavities, and we can test models. And then we will be doing axion astronomy. If that can happen, it will be really good. And I probably wouldn't have to be so hard writing grants as much anymore, like all you Ausgrad people. But what we want to do is beyond the standard quantum limit, and we know how to do that. The Yale people have already done that, and we're set up to do this year on our organ Q experiment. It will be running a squeezed state output this year, and start taking data, and we hope and we'll get better sensitivity towards a QCD axion. But what we really want is these single photon detectors. We're looking at these systems, the Josephson junction systems, as a single photon counter. We've been doing that quite hard work with Graham Flower, but we've started this collaboration with Emmanuel Fleuren, and this group has really made the first viable photon counter. I don't know if you've seen this work, but there's Patrice Berthet at Saclay. You know, the French guy that got the Nobel Prize, Deveray, was this guy's PhD supervisor. Okay, So now we bring all three Nobel Prize winners into the story. And they've built this single photon detector, which is amazing. And I first saw that last year in Helsinki. I contacted them. Emmanuel is actually in UNSW at the moment, working with Andre Morello. He's already come to my lab. We brought him to the lab. All French like good meals, so we took him out for a good meal. And that seemed to work because now we've got a good collaboration and we'll be doing work. The moral of the story, if you're dealing with French, always include a good meal. But here is ADMX. I'm really excited about these single photon counters because in the end, I think that's how we get to the QCD axion limit at 15 to 50 gigahertz. These will work, and they've got a startup company, and in the future, we'll be able to get them. And we're going to be part of their pilot program to test their devices. So ADMX is here. It shows you it's a much bigger system because it's much lower frequency, and it's been taking data for a long time. Here's some, and now we joined in 2019, and now Ben has created a group at Swinburne. This is a direct outcome of the Dark Matter Center, giving the ability to create a second group at Swinburne with Ben, who's a DECRA fellow out there now. And you can see ADMX is tested down to these axion limits for GA gamma gamma, and it's got funding by the DOA to 2029. So we hope to be involved with them to 2029. Our centre will probably extend to out there. So and then whatever happens after that, we'll get more funding to keep going. So here's a bunch of papers that have happened since we've joined. And the next system is we have to keep scaling up. The problem is as you go up in high frequencies, the volume of your cavities go down. And so you're going to have to start having more than one cavity in your search to get to the sensitivity you want. We've also developed these, I can now start talking about these up conversion experiments. We've done some of those experiments. Kat did a PhD on that and got some interesting results and set limits. We built these low noise oscillators to excite these modes. But the most interesting thing we did was we created these resonators with non-zero helicity. In other words, they have modes with right-handed and left-handed properties, and that's because the boundary conditions are helical, they're twisted. And that enabled us to get modes, like in a lot of systems, these type of systems that have helicity are in lower dimensions. This is over the volume. We get non-zero E dot B, imaginary E dot B. And that makes it sensitive to axions. We've also started to learn about these systems. We've published more papers. Jeremy and Emma have got an Australian Economic Accelerator grant to look at using these to sort helical materials, which is quite interesting. But understanding these systems has been quite difficult because they have some topological properties. And it's, anyway, it's been an interesting time to understand that physics. But what I'm interested in mainly is looking for dark matter, and these devices, if you can make them, the two frequencies are the same, and when you subtract one number from its same number, you get zero. So that means you're looking for ultralight axions when you scan in the Fourier space. So very low mass axions, we're talking about minus 21 eV and things like that in the spectrum. So we've started this collaboration with Pashupati from Jefferson's Labs, and they've just built us a twisted resonator from superconductor material. We had to come up with a novel way. I can't show that at the moment, but because it's a novel design. But we've 3D printed these, and now we're making them from some of the best cavity materials. We can go up Qs of 10 to the 10. So we've got Emma has got a CSIRO scholarship to go to Jefferson Lab and test these, and we're sending Rob as well, who's building low noise oscillators and testing these high Q cavities to Jefferson Lab. And what we do is we'll make oscillators out of these, and we've worked out the signal to noise ratio. I won't go into the details, I don't have time, but the point is you've got to look in the AM noise spectrum because this is you generating power. It's in the AM noise spectrum, so you've got to have low AM noise oscillators and high Q cavities, which have helicity, and you can do ultra low axion searches. We're talking about minus 10 to minus 25 to 10 to minus 16 that you could, in principle, look for axions. There's no other way with the coupling to the photon parameter. There's other ways looking at spins and things like that where you can look down that low. We've also got these experiments that there's this idea if the monopole exists, you've got duality comes in and there's other paths for coupling. And this has been proposed. And we come up with an idea to look for gut scale axions with a high voltage capacitor. The interesting thing, if the monopole exists, you've got this extra term, monopole term plus the geometric mean. And it's alpha squared times easier to measure the QCD axion through this portal. So that's why we want to do it. But what it means, if that exists, this assumes that the gut scale monopole exists, which a lot of people think does, but it means this has all been ruled out and must be gut scale at lower masses. And so we come up with this idea to have a high voltage capacitor. In this, for this experiment, you have a high voltage capacitor, and that creates a magnetic field rather than the other way around. But you have to put a magnetic circuit around your capacitor, otherwise the fringing fields will cancel. So this way you can have the electric fringing field, and the magnetic field gets converted and gets sucked up by this magnetic circuit. And you can either use a SQUID low impedance amplifier or maybe a high impedance amplifier with a large coil to this experiment. And in this paper, we predicted we could easily get to this QCD axion limit with reasonable physics assumptions. But our first experiment, we have a PhD student. We're just using something we can buy from DigiKey, which is like a transformer with a gap. We put a capacitor there. We put some coils here. We put high impedance amplifiers here, and our first experiment will be at room temperature. And once we got that working, we can go cryogenic. And we should be able to put limits up here. And if we get a bigger system with cryogenic, we can do this. Okay, now I want to talk about, that's axion experiments. Now I want to talk about these acoustic experiments. This is called the multimode acoustic gravitational wave experiment, MAGE. We put these papers out, which you can use these systems to look for scalar dark matter or high frequency gravity waves, or even gravitons if gravity waves exist out there. We call this a multimode gravitational wave experiment. As I said, we've got this SQUID amplifier hooked to this quartz resonator, which is the phonon equivalent of every Perot cavity. And we have two of these because when you do a search for some fundamental physics, if you just have one, in our first one, we had one, and we saw some rare events which were quite large, but there's no way you can tell what they are. We just reported it, and there was a bit of discussion on that. But now we've got two, and we can actually see what they are. We can have an idea what they are. And so MAGE's main goal features was two identical quartz board detectors, maybe more. And we use, in our first experiment, we just used the lock-in. Now we use an FPGA. With the FPGA, we can mimic 32 lock-in amplifiers. So why buy 32 lock-ins from Stanford where you can have an FPGA and need someone smart to program it? And we can look at 16 modes per crystal. So wider bandwidth SQUIDs we've got now, we go up to 200 megahertz, not in this last run, but we do have them now. And we want a cosmic particle veto system. We haven't implemented that yet. And now we've got this operating at millikelvin. We haven't reported that anywhere. I can tell you now it's operating at millikelvin, but our last publication didn't show that. And what we can do with this is look for, in our latest paper, we put limits on primordial black holes, but primordial black holes can be dark matter. So we use MAIDS to constrain primordial black hole mergers. So this is the paper that we just put out in December. We could put limits on black holes of this solar mass, 10 to the minus 4 to 10 to the minus 9, and we could put, and we can put a merger per year, as constraint of a merger per year about to the distance of the solar system. And we can say, in addition, we exclude significantly rare and strong events that we observed in the previous experiment as non-gravitational background signals. Because when we use our multiple detectors, we still saw these rare events at high energy, but they never correlated at the same time in the crystals. One could ask why we wouldn't do that at the start. That's because at the start we only had one and we just did an experiment. So this is the experiment. We have these two detectors in the same cryostat. We've got 61 days of non-continuous data collection. We use optimum filtering, the same as what we used in the BAR project. Coincidence, we do coincidence analysis, which removes all non-gravitational background signals by coincidence analysis. And we see high energy events, but they never occur at the same time. Here's an example of a histogram of the events. If you do a histogram of the events, you typically, with thermal noise, you get a histogram like this, which tells you the temperature, and then you can see high energy events out here. This shows you the mode temperature, and when we apply the optimum filter, our effective temperature goes down to 55 millikelvin through the filtering, but we see some events, but they can all be taken out with the coincidence analysis, where we look for where we optimize an optimum filter for the response we expect from a primordial black hole. And that is, it really looks like a burst because it only experiences a few microseconds in the detector as the primordial black hole would merge. So this is our limits. And this is what's been done by LIGO, and this is what we could do with single modes. With our multiple modes, we can look for the merger because it changes in frequency, so we can use more than one mode to check and get extra exclusion from multiple modes. I won't go into the technical details. So now the next stage is networks. For example, we know a gravity wave is better to have more than one detector. But there's also these predicted coherent sources of dark matter out in the universe. This gives you the line shape of the galactic halo due to virialization. And here's some predicted coherent sources coming from somewhere in the universe, which we can use, which we can look for. We see here that we've built this in Perth. We now got we got funding to build one in Melbourne, and we moved one. There's Ben got a dilution fridge there, and we can put one underground if we think these high energy events may be cosmic rays. If we have one installed, it might be useful to in the underground lab to rule out. And there's also one in Milan that just got built. We had one of their students from Milan come and work with us for a year, and now he's doing it. He was a master's student then and got his master's. Now he's doing a PhD in Milan, and they've built a similar detector. And then we can use the Axion detectors too with ADMX. With our organ Q experiment, we're planning to do that, and they have an experiment at a similar frequency. But there's now this GravNet proposal, which got a lot of funding from the ERC Synergy Grant. They've got a lot of funding from now into something like 2032. To build a global high-frequency gravity wave network. And it will include us over here and all these places around the world, including Abu Dhabi and China and places in Europe. This is Tenerife and Fermilab. So I can finish there and finish on time. Hopefully I finished on time, with plenty of time to go and not to hassle when the next group comes in. And there's plenty of time for questions if anyone wants to ask.
Questions? Do you hear me?
Thanks for that very entertaining talk, Mike. promised I would harass you about the high frequency gravitational waves before, so here we are. Um, as the frequency of gravitational waves goes up, space becomes more stiff, and so more and more energy is required to achieve the same strain. And Paul Lasky and I have argued in a paper published in PRD that the current generation of detectors, if they can detect megahertz and gigahertz gravitational waves, that would imply that there is 10 to the 8 times more energy density than the energy required for a flat universe. So while I take your point about 1,000 experts, don't we have, from our belief in cosmology, some constraints on high frequency gravitational waves before looking in a megahertz or gigahertz detector?
Yes, so I'm no theorist. I know Tony Gargetta was here, and he was saying that they're very well motivated, some stochastic backgrounds and things like this. But most models of high frequency gravity waves are beyond standard model physics. So my argument would be there could be some coherent source at some frequency that is due to some beyond standard model physics, whatever it is, might be out there, and if we detect, would be a huge thing. So there's 2 points to this argument. One, if you read those white papers, there is a bunch of proposed sources for beyond standard model physics and some stochastic background. And I mean, when we looked at the photon spectrum, there was a unexpected high energy events as well. So it wouldn't surprise me and there's a lot of things we don't know about the universe. We don't know why it's accelerating. We don't know about dark matter. There's so many unknowns. I think if we have the technology, we have to look. I think we have to look, and if people have the ability to look, and especially since these other detectors can put constraints on other things and look for dark matter, I think we should look. Because if you do find something, it could be the solution we're all looking for. So I would say that these experiments will be looking for dark matter and high frequency gravity waves. We might as well do them. It doesn't cost much. The experiments are much lower than a Large Hadron Collider, for example. We're building tabletop experiments we're training students to use dilution fridges, which is very important for the next generation of superconducting devices. We're using these as we build. You can see these single photon counters. We're going to be one of the first customers for this. That will generate this company, which Emmanuel's building. I think this is going to revolutionize a lot of areas in physics. So we must do it. We mustn't do it not just to be inquisitive, but we're going to develop new technologies. For example, I have 13 patents. I never desired to have any patents, but I have 13 patents. I never desired to do anything that was translational, but I have. And when you do this stuff, you naturally do that, and that now enables the people who are coming through to get jobs. I think this area is a win-win. Not for developing technology, for putting money into science. It's not like we're putting billions of dollars into things. We're using dilution fridges. Small budget doesn't take much. You can get a dilution fridge here. You can start doing this stuff. It's not that expensive.
Okay. Any other questions?
Sorry for making you run up here. Thanks for the talk. So, as someone who's done quantum sensing but hasn't done quantum sensing for fundamental physics, I was wondering if, I guess what you've learned from looking for fundamental physics, and if there are any lessons that, or techniques or something that you'd like to share with, other areas of quantum sensing. If that makes sense. I don't know.
Yeah, definitely. I just think you have to look at the Nobel Prize, right? The Nobel Prize from John Clark, John Martinez, and Michel Deboré, who are now big names. They did this experiment, published in PRB. You know, it's a good journal. It's not the most outstanding. It's a good journal. That won the Nobel Prize. I mean, that's amazing. When you look back at that work, you can see why, from our perspectives, we can see it won the Nobel Prize. Back then, it was just fundamental physics. And that's what we're doing. So, and in my perspective, when you look at these twisted resonators, for example, we wanted to make a resonator with non-zero E dot B. We eventually succeeded, but it took us 3 years. We were doing the wrong things, wrong simulations. Eventually, we were understanding what we were doing, and eventually we turned it into these twisted structures. And then when we saw it had something, first we didn't understand it. Then we finally understood it. So you get a when we did it, it wasn't obvious. So we had, so it turns out, I didn't go into this, but it turns out you need a unity aspect ratio. Why do you need a unity aspect ratio? Because you want degenerate modes. Just like in a hydrogen atom, you have degenerate modes. They hybridize, and you get stark sensitive atoms to electric field. That's because so you want these normal modes in a triangle resonator. You choose triangle because if I twist a resonator, if it's circle, nothing will happen. So the least amount of sides gives you the biggest helicity. We soon learned that too. So as you twist it, what happens is these two modes mix, and they now become a basis of left and right-handedness. We would have never done that research if it wasn't for axions, if we weren't trying to get non-zero E dot B. But eventually we built this, and it looks like there's some spin-out technologies, right? So my experience along the way is that I got 13 patents. Another one was on these magnons. We developed these magnons with these reentrant cavities, and we got this really huge coupling. My experience is that when you're doing this basic research and thinking of ideas, you come up with these new ideas, and that you can see all these spin-offs, right? And we actually put in a bid for a centre called Quantum Innovations for Discovery Science. I thought it was the best thing, but anyway, it didn't get funded. Just didn't make the EOI. But this is basically it. When you're doing basic research, you come up with new ideas that would never, ever been thought of if you're not doing fundamental physics. And the proof's everywhere in the past. And the proof is in my, actually, career, too. I never wanted to do anything commercial, but I've got 13 patents, and I have. That was sort of just because it happened, and you take the opportunity, because that's the way you keep people in your group employed. So I think there's a huge opportunity in Australia. We should fund projects like this because we're training people in this quantum sensing. We're coming up with new ideas. We need to double the discovery budget because there's so many ideas not getting funded. So many good ideas. Everyone's coming up with them all the time. Imagine if we got all the funding for everything we could do. We'd be superstars,
Any other questions? I have a question. What else could you do with these devices except for the searching for fundamental physics?
Well, yeah, so there's these devices. We're building lots of devices. I think these single-photon counters, which have been developed by these Paris guys, Patrice Bertet and Emmanuel Fleurin, I think they're going to revolutionize sensing, in my opinion. And it will enable us to get the QCD axion level. So when you develop something like that, that's superconducting technology. And this is where I think it's right about building on other Nobel Prizes. I believe that from these devices that we're building, because we're seeing things like, high-power lasers get Nobel Prizes and things, the devices that you build from them will start getting those. I think there's lots of things.
Okay. Thank you. So let's thank Michael again.